In this video, I'm going to talk about how to perform eigenvalue analysis by using partial differential equations manually. For this purpose, I'm going through a simple example. As you see here in the left-hand side at the top of the page, we have a two-story concrete frame building. The height of those stories are 3 meters, and the mass is lumped at the story level as M1 and M2, correspondingly equal to 80 tons and 50 pounds. And if you look at the column sections, you will see there is concrete square column, and the dimension is 350 millimeter, and the modular of elasticity is 20 gigapascal, which means it's concrete. The beams are rigid and the diaphragm is rigid, so it means that you can assume that this structure has only 2 degrees of freedoms. We discussed about this simplification during the past lectures, and if you accept this simplification, you can come up with this fact that the stiffness for each individual column can be calculated as 12 E, this is I, and this is cubic L. And because we have 2 columns in each story, it should be multiplied by 2, and the whole term, which is this one in terms of Newton over meter, is the stiffness for the first story, which is equal to the second story because everything is similar in both stories. And for mass matrix, you can write it like this: M1 is the mass in the first story, and M2 is the mass in the second story, and these are 0. It's a diagonal matrix. So 80,000 kilogram and 50,000 kilogram, just to comply with the SI units here. And for the stiffness matrix, we spoke about this during the past lectures. You can write it like this, and K1 and K2 are respectively the stiffness for the story 1 and story 2. If you have any kind of structure like this, but more than you use, if you have n stories like this, the mass matrix is still diagonal. M1, M2 until Mn are the masses for story 1, 2, 3 to story n, and everything else is 0 here and here. And the K matrix, the stiffness matrix, can be written like K1 plus K2. Here you can see K2 plus K3, K3 plus K4. It goes down here with the same pattern, except for the last term, which is Kn, which is the stiffness of the roof floor, the top floor. And this diagonal has an adjacent diagonal here, like minus K2, minus K3, minus K4 goes to minus Kn, and the rest are 0 here. So you have only the main diagonal like this and one line here, and everything here should be mirrored for the bottom part of the matrix, which means the matrix is symmetric. And it means that in total you have only 3 lines of numbers, one line here, one line here, and one line beneath the main line. So this is the stiffness matrix, and this is the mass matrix. When we assemble the mass matrix and stiffness matrix, we can start the eigenvalue analysis by setting the determinant of the matrix K minus omega to M should be 0. K and M are the stiffness and mass matrix. They are 2 by 2 here, but omega is a scalar and unknown. The aim is to calculate the omega here. So what I've done here is multiply omega 2. If the pen works here, I don't know. The aim is to calculate this omega, and what I've done here, I've used this mass here and multiplied it by omega 2, then with a minus sign here, then added with the K matrix, which is this one. Actually, this is this one. And I came up with this part, which you have omega 2 in it as the unknown you're looking for. And you want to calculate this as the determinant of this matrix should be 0. For the 2 by 2 matrix, it's very easy to calculate the determinant. So it's very easy to multiply these two together minus the multiplication of these two together. So if you do that, you will come up with this sort of omega 4 and omega 2. It's like you can name omega 2 equal to lambda, just the name, and calculate the lambda and then calculate the omega 2. It's easier. If you solve this equation, you will come up with two values for omega 1 and omega 2. Always just name the lowest, the smallest value as the omega 1 and sort them out, and the bigger one would be omega 2. So with this trend, you can calculate T1 as well, because omega is radian per second, but T1 is in terms of seconds. It's 2 multiplied by pi divided by omega 1. Simply, you can calculate T1 equal to 0.523, and T2 will be 0.215 seconds, and T1 is called the first period of vibration, and T2 is the second period of vibration. These two, T1 and T2, are called eigenvalues of this problem. For each eigenvalue, we have eigenvectors as well. So the right-hand side here, if you take a look at here, the aim is to calculate the eigenvectors of the problem. And for that purpose, again, copy and paste this matrix here, which is k minus omega 2m, multiplied by phi, which phi is the eigenvector, equal to 0. So we need to repeat this for 2 times. This is 1 time and this is 2 times. For the first attempt, if we substitute the omega equal to omega 1, for now we have the omega 1. Omega 1 is 12.014 radian per second. So I just substitute omega 1 into this matrix, actually this matrix, and I will come up with this matrix multiplied by phi 1, 1, phi 2, 1 equal to 0, 0. These are just names because I want to calculate phi, which consists of phi 1 and phi 2. I just name them like this. The two indices indicate the row and columns. And if you take a look at this equation here, it's like a system of equations, actually, 2 by 2. And the 0 and 0 are the obvious solution for this system of equations, which I'm not looking for them, because 0 and 0 means nothing, no movement, no deflections. I'm looking for non-obvious solution for this system of equations. So what I need to do is to assume one of them and calculate the other one. That's why I assume this one equal to 1. You can assume equal to whatever value you like, but it's more convenient to take this as 1. And if you do that, you can use the first equation to calculate the second one. Like this number multiplied by 1 minus this number multiplied by phi 2, 1 equal to 0. And that brings you to phi 2, 1 equal to 1.48. So if you this is called the first mode shape of the structure, and it means that, like, if the structure is this one, the red one. The blue one is the first story goes for 1 unit in the right, and the second story goes as 1.48 in the right hand side, and the deformed shape of the structure calls the first mode of vibration. If you repeat the whole process for omega equal to omega 2, which is 29.259 radian per second, you will come up with this one. And again, I will set this one to 1, and I will calculate the second one, which brings me to calculating the second mode shape, which is equal to the vector of 1 and minus 1.08. This means that the first story goes 1 unit to the right, and the second story goes 1.08 unit to the left because it has a negative sign. So this is called the second mode of vibration, and just to be sure that everything is calculated correctly, we have a control point here just to see if we have done any mistakes or not. If you have noticed, in both iterations we have used only the first equation here, but we didn't use really the second equation. So for example, here if we use the second equation, like this number multiplied by 1 plus this number multiplied by 1.48 should be 0, which is 0. And we have another equation here, which means that this number multiplied by 1 plus this number multiplied by minus 1.08 should be 0, which is correct. So with these two controls, we'll be sure that our numerical calculations is okay. And with this kind of analysis, we proceed to calculate the eigenvalues in the left hand side and eigenvectors in the right hand side of the equations. It's worth noting that the first assumption for phi11, or in the second iteration phi21, is I take them as equal to 1. You can take them equal to whatever you want. For example, in the first attempt, here, if you assume phi11 equal to minus 1, you will come up with minus 1 minus 1.48. So it means that the first story goes to the left as equal to 1 unit, and the second story goes to the minus 1.48 to the left. So these mode shapes are relative, they can be, for example, the first mode shape can be 1 and 1.48, or can be minus 1 minus 1.48. These mode shapes are not exact deformation of the structure, as I explained in the last lectures too. They are forming the final deformation of the structure. Actually, the final deformation of the structure is a combination of mode shapes and some other factors coming from the external forces. So as you see, the mode shapes are only depend on they really depend on only stiffness and mass. So they are coming from the nature of the structure, not from external loading. So they are somehow the inherent characteristics of the structure rather than expressing the effect of external impacts of action in external loads you have on your structure. So that's why when you have some external forces, the final deformations or internal forces will be calculated by combining the mode shapes of the structure with some other factors which usually come from external forces. And if you remember, we talked about it during the lectures in a way that the first mode contributes to the final deformation of the structure more than 90% or sometimes 95%. in most of the common structures and symmetric structures. Um, it means that really, if you take the first mode into account only, you're accounting for something like 90% of the whole answer and solution of the structure. That's why the first mode of the structure is the most important one rather than the second, third, fourth, and etc. We will see those in the following videos as well, and we'll compare them with other approaches later on. Thank you for watching this video and proceed to the next one, please. Thanks.